Okay, welcome to the Southampton Science and Engineering Festival 2022. This is an event organized by the Public Engagement with Research Unit at the University of Southampton. It runs from the 11th to the 20th of March, so it started this past Friday. There are a lot of good events taking place, not just this one, so I encourage you to explore the full schedule of live talks and exhibits. If you want to comment on social media about today's event, please use the official festival hashtag #SOTSEF. Okay, if you see me looking over to the side, that is me looking at the live comments. So if you do have comments, just put them in the chat box, and I'll try to reply to them as I go through the talk. But it may be a bit of a delay, or I might wait until the end of the talk to answer some of them. Okay, so hopefully you are seeing my slides. I'm not currently seeing them. There we go, perfect. Okay, so my name is Adam Pound. I'm a Royal Society University Research Fellow at the University of Southampton in the Mathematics Department. And I work on these things: black holes, gravitational waves, and the equivalence principle, and related topics. So I'm going to guide you through kind of an assortment of topics that you might not necessarily see joined up in a typical talk about gravitational wave astronomy. But hopefully by the end, you'll get a nice picture of why I called this an adventure in space-time. This is really a big, grand, ambitious venture with a lot of pretty wild stuff going on. So let me lay out just the rough structure of what I'm going to talk about. I'm going to start with a pretty whirlwind tour of gravitational wave astronomy. So if you don't follow everything I'm saying at the beginning, don't worry about it, because in the second portion of the talk, I'm going to loop back and try to give you more of a sense of what all these things really mean. So black holes, gravitational waves, and again, the equivalence principle. Then once, hopefully you've understood all that, we will then move on to these specific kinds of events called black hole binaries, where you have two black holes. A bit of details about that, and what is next? What is the future of gravitational wave astronomy? Because it is a big venture, and it's just started. There's already decades of work being planned, with a lot more interesting and novel stuff coming out. Okay, so let's start with what is gravitational wave astronomy? Well, first, let's just take a step back to conventional astronomy that hopefully you're all familiar with. This is astronomy that we see just with light. We have a big telescope and we just see visually the same kind of things we see as we look around, just light coming into our eyes. Now, it might be something a little bit different than light. It might be electromagnetic waves that we can't see, like radio waves. But it's all coming from electromagnetic waves traveling through space from pretty crazy looking things like this. So this is an image from the Hubble telescope, which was launched a few decades ago. And probably if you've seen a spectacular image from outer space, probably it's from the Hubble telescope. And you might have seen recent news that NASA has launched this kind of the sequel to the Hubble telescope, which is called the James Webb telescope. So we see a lot of insane looking things, pretty amazing things with conventional astronomy. But because it's all coming to us through this particular medium of electromagnetic waves, we actually miss a lot of the most dramatic things that are happening out in the universe. Because a lot of the most dramatic things don't actually involve any emission of gravitational waves. So specifically things that are just purely driven by gravity without any electromagnetism involved. Now this is important because the motion of everything we see out in space is really dictated by gravity. That's really the dominant force governing the whole shape of the universe, everything in the universe. And we think that gravity is described by this theory of general relativity that Einstein came up with just over 100 years ago. And I'll spend a lot of this talk discussing general relativity. Now, up until recently, general relativity, Einstein's theory, had only really been tested. We only knew it was correct in very limited circumstances, really primarily within our solar system, by looking at the motion of planets, by looking at the motion of light in the solar system, and actually with things like GPS, global positioning system, that actually uses general relativity. But this whole solar system, everything we see around us, is a very particular kind of system where gravity is relatively weak. It's a very, very weak setting as compared to the most extreme gravity out there in the universe. So until recently, traditional astronomy hadn't really told us much about whether Einstein's theory was correct or not. It hadn't really told us much about the nature of gravity out in the universe. And this is because many of the most dramatic predictions of general relativity, such as black holes, are pure gravitational phenomena. They have nothing to do with electromagnetism, and we just can't see them with traditional instruments. Okay, but even before we get to gravitational wave astronomy, we did get some idea of things like black holes with conventional astronomy, basically by observing that there must be something in some locations that we just can't see. And it's just black. So this is an image of the center of our galaxy, the Milky Way. And unfortunately, there's some lagginess in my internet today, but hopefully this movie runs all right. So you can see this white blob zipping around something. It's coming in and then zipping around something. So that's a star in the center of our galaxy, and it's zipping around something, but something we can't see. So we think that it's a massive, massive black hole at the center of the galaxy that's about as big as our sun at the center of our solar system, but about 1,000,000 times heavier than our sun. So an incredibly heavy object at the center of the galaxy. Now, by observing the path of these stars, we can trace out their path in time. And so this is the motion of the 3 closest stars to the center that we observe. This is just a drawing. This isn't actual observed data like the previous movie was. But you can see clearly that these things are orbiting around something right here. Now, in this picture, the something right here is in blue, but as I showed in the previous movie, we can't actually see it. It's just something black. So based on the path these stars are taking, we think that there's an incredibly massive black hole at the center of the galaxy. And in fact, we think that almost every galaxy has a supermassive black hole at its center. Now we can get a bit more of a close-up view of a black hole using what's called the Event Horizon Telescope. So the Event Horizon Telescope is something that's basically turning the entire planet Earth into an enormous telescope. And because it's so enormous, we can get very fine resolution. And so unlike where we saw those stars zipping around, we can look much, much closer and kind of see a black hole. Again, what we're seeing is just the black thing in the middle. We don't see the hole itself. We see what's happening to stuff around it. In this case, the light that's coming around it. So this is a black hole in the center of not our galaxy, but a neighboring galaxy. And this image came with a lot of fanfare as the first time we've seen a black hole. And with this kind of image, we do get some sense of whether Einstein's theory is correct in strong gravity. But with these kinds of instruments, we can only see fairly close supermassive black holes at centers of galaxies. We can't see any other kinds of black holes that are out there. And the data that we get from this is actually very heavily dominated by astrophysical uncertainties. When we're trying to figure out or deduce what is the black hole in the center here, we need to make some assumptions about the behavior stuff around it. And the uncertainties in those assumptions are very big. And so we can't actually deduce that much about the black hole in the middle. So when does that all change? That all changes when we have gravitational wave astronomy. This is where we're just seeing pure gravity. We're not relying on light coming to us. And because of that, we can see new things that we could not see previously. So this first detection of gravitational waves occurred 6 years ago, at the very end of 2015. And as I said, all these things I'm flashing through right now, I'm going to explain in much more detail in the second portion of the talk. But basically, what you're seeing here is little wiggles in space-time itself. Space-time is kind of wiggling a little bit because of something that happened very, very far away, roughly 1 billion light years away. So this is little wiggling that was detected by this detector called LIGO. This is over a pretty short time span, about half a second. And with a lot of fancy mathematics developed over about 30 years, we could deduce from this wiggle what created the wiggle. And what it created it was the motion of two black holes going around each other. These black holes are not the supermassive black holes at the centers of galaxies. These ones were about 30 times as massive as our sun. So very, very massive, but very, very tiny compared to the black holes at the center of a galaxy. And so what happens is these two things orbit around each other. Because they're emitting these gravitational waves, these little wiggles, they lose energy. So they lose what's called kinetic energy. Kinetic energy is what is keeping them moving on a spiral like this. And they're losing that with time because it's being removed through gravitational waves. Because of that, the spiral is getting tighter and tighter and tighter until the two black holes actually just merge and form a single black hole that's roughly twice as big as one of these black holes you started with. So this was the first time that we'd actually seen something like this, where we see something that's pure gravity, and it's in the strongest fields we can think of. It's the black hole. It's the strongest gravity possible. And so this was a huge, huge breakthrough in science. But that was just the beginning. Now we see these things all the time. When these detectors are up and running, they're detecting signals about once a week, so very, very frequently. What I'm showing here is just the signals for the first couple of years. We've now seen almost 100 signals, and each of them comes from a system like this, where we have two bodies going around each other. They have to be super heavy, super dense bodies, which means in practice, they're almost certainly black holes or something called neutron stars, which is basically the densest star you can make. So we've seen a lot of these things now, dozens and dozens, almost 100. Now that was a whirlwind tour. I was going through a lot of things quite quickly. So now I'm going to take a step back and really explain what we're seeing here and basically what it tells us about gravity and the universe around us. Okay, so taking a step back to the most basic things. So I said that Einstein told us that general relativity is the theory of gravity, and as far as we know, he was correct. So what is general relativity? It's a theory that says that the gravity we observe, things being pulled together by gravity, is just a manifestation of what's called space-time curvature. So we can think of all the collections of points So all the locations, all the instants of time, everything, every little event in your life, every little event all around the universe forms a smooth shape called spacetime. So it's not space, it's not time, it's the collection of all the possible events in the history of the universe. And gravity is a manifestation of the shape of spacetime. So we typically introduce this concept using this analogy of a rubber sheet. So let's imagine this is just a sheet you stretch out, it's rubber. And when you put something heavy on the sheet deforms due to the heavy body sitting on it. And once you've got this thing deformed, if you have something else moving around on the sheet, its motion is going to be determined by the shape of the sheet. So let's say you release some little body here. From rest, it just follows this line down to meet the star that I've put here. Or you can imagine giving this same little body a little kick so that it's moving along this circle. And again, sorry for the laggy internet today, but you can see it's now just following the circle, just like it would if you had a real rubber sheet there. And this is how gravity works, except it's not a rubber sheet, it's space-time. Okay. Now, how does this tie into what's called the equivalence principle? Well, I said that, okay, if you deform this rubber sheet and then you just imagine, letting a body move around on it, it's going to move in a particular way based on the shape of the sheet. But what actually says that a body has to be dictated by that sheet? Why can't it just jump off the sheet and do whatever the hell it wants? It could do anything. Well, what dictates how it moves on that sheet is this thing called the equivalence principle. So the equivalence principle is a key idea in Einstein's theory that says if you have a freely falling observer, so not an observer standing on the Earth, but an observer that's just falling in gravity, like say, you're floating around in space, orbiting around the Earth. Then in a little patch around that observer, the observer should see everything behaving just as if he or she were in just totally empty space with nothing around him or her. So this is a key principle that if you're just falling, you're out in free fall, like say you see those pictures or those movies of astronauts in the space station where they're just floating around, what they observe is in a small enough patch around them, indistinguishable from what they would observe if they were just in totally empty space with no gravity at all. So let's say this little astronaut is that observer. And they're in free fall in gravity, so they're just following along this straight line. And then another body passes by them that's also in free fall, but it's moving along this curve. Well, if physics in this little patch is supposed to look just like as if you were in empty space with no gravity, then what does that mean? Well, that means that, if I can move forward, if you zoom in on this little patch around the astronaut, as far as he's concerned, he's moving on a straight line. And as far as he's concerned, this ball that's moving around in the circle is also moving on a straight line. Because if you zoom in on a small enough little patch, these curved lines look straight. And, okay, what does this have to do with the equivalence principle? Well, the equivalence principle says that this is what has to happen. This is how things have to move in a curved space-time, because things have to look locally in a small little patch just how they would in a totally empty space with no gravity. And in a totally empty space with no gravity, if you just give something a little kick, it's going to keep moving in a straight line at a constant speed forever. And that's this little straight line. So locally, you need, in small little patches, you need to have straight lines free particles that are just moving around freely in gravity have to be moving on straight lines in little patches. And basically, if you join all those little straight lines together, what they form is, for example, this curved path, or this one that's going down into the star. So these lines, these curves, are something called geodesics. And they're basically the straightest path you can get on a curved surface or in curved spacetime. Okay, so the equivalence principle tells us how things move in a spacetime once you've deformed a spacetime. Now let's back up to another concept that I introduced, which is a black hole. Now, I'm sure all of you have heard about black holes, but maybe don't actually know what it is. So remember, if I put a massive star here, it deforms this surface. Now, a black hole just keeps deforming it. It's just a hole in the surface. There's nothing here. It just keeps going down and down and down until the curvature actually becomes infinite, becomes infinitely curved once you get sufficiently far down. And why is it a black hole? Well, the idea is if you fall sufficiently far into this hole, you can never get back out. No matter how fast you're moving, no matter how strong your jetpack is, you can never get back out. And so even light, which is the fastest thing in the universe, cannot get out of the black hole. And that's why it's black. There's no light coming out, so we can't see it. Okay, I do see I'm accumulating some comments here. Okay, there's a question. How are gravitational waves produced and projected so far from where the source's gravity has noticeable effect? I will explain that once I get back to gravitational waves. So just hold on a second. And why roughly twice as big? So I said that when we had these two black holes moving around each other and they merged to form a single black hole, the final black hole at the end is roughly twice as big as the individual black holes we started with. And the question is, why roughly twice as big? Is some mass lost when the black holes merge? And if so, how? Yes, the answer is yes. The mass, or the energy, is actually being carried away in the gravitational waves. So when they merge, there's a burst of gravitational energy that takes mass away from the black holes. Okay. So now that I've introduced how things move in space-time as dictated by the deformed space, or the curvature of space-time that's caused by massive bodies, and I've introduced the nature of a black hole as something that the gravity is so strong that nothing can ever get out of it. Now let's go back to this image that was produced from the Event Horizon Telescope and think about what we're actually seeing here. So what we are seeing, for example, this light here is actually light that started from behind the black hole, right directly behind it, and passed over the top and then came towards us. So the path of the light gets curved by the presence of the black hole, the gravity of the black hole. And so what we are seeing here is what's behind the black hole. So here's a schematic picture illustrating that. So here we are on Earth as an observer. Here's this big black hole. And if light is emitted from behind the black hole, its path gets curved around the black hole and then comes out here. Or similarly, if it comes out this way, it comes from the back, comes out, gets curved, and meets us over here. And so this ring we're seeing on top and bottom is actually what's behind the black hole. Okay. Now let's go back to the case that we see with gravitational waves. This is when we have two black holes moving around each other. Well, what does the space-time look like in a scenario like that? Hopefully this movie isn't too laggy. Let's see. Okay, so this is an image or a movie that's not something we actually literally see. This isn't real experimental data. This is just a numerical simulation of what we would see if we had two black holes orbiting around each other and just a whole bunch of stars in the distance behind them. And you see everything is getting deformed behind the two black holes. And that's due to the bending of light as the light passes around the black holes. Okay, there's another question in the chat. Why doesn't it fall into the black hole? Well, some of it does. So if we go back here, some light that's not, not in this path, but a path like a little bit to the right will fall into the black hole. Lots of light will fall into the black hole, but not all of it. Some of it will just go around the black hole. Because if you're outside the black hole, gravity isn't any different than if you're outside the sun. It's the same physical effect. And not everything falls into the sun. You can have things orbiting around the sun forever, and you can also have things orbiting around the black hole forever. It's only when you get sufficiently close, when you're actually inside the black hole, behind what's called the event horizon, that you can never get back out. Okay. So the movie I showed was what you would kind of see visually if we had powerful enough telescopes that could look at two black holes moving around, and we have a lot of stars behind them to give us basically the bending of light. Now, what about gravitational waves? So this is a movie not showing what light does, but actually directly showing the curvature of space-time. So fortunately, this one's not too laggy. So we have these two black holes moving around each other, and they're deforming space-time as they move around. And let me show that one another time. So it's like two bodies moving around in a pond. You're deforming the surface of the water as the two bodies move around in the pond, and you're sending out ripples. And so what we're seeing here is ripples in space-time curvature. Now, going back to the question earlier, the question was, how are gravitational waves produced and projected so far from where the source's gravity has a noticeable effect? Okay, so near the black holes, those waves are big, really, really big. Each of those black holes, say that the first two black holes that were seen orbiting around each other, each of those was maybe 10 kilometers wide. I'm probably a bit off in that. They're pretty small, but as big as a small town, 10 kilometers wide. And you're seeing big, huge waves on the scale of the same size as the two black holes. But as they propagate outward, they get weaker and weaker and weaker. And by the time they reach us, a billion light years away, they are really, really, really weak. So I'll get to that in a second. But let's think about, say we're some distance away from these two black holes, and the wave passes by us. What do we actually physically observe? Well, let's set up a ring of freely moving particles, or just say little physical orbs, whatever you like. And remember I said that the space-time curvature dictates how these things move. And so when the wave passes through, what happens is that this circle gets deformed, it stretches, shrinks, stretches in this particular pattern. So the idea of gravitational wave astronomy is this. The idea is to measure this stretching and shrinking. So that's what we're going to get to in the last portion of the talk. So we've got these two black holes going around each other. And with current detectors, with the detectors on Earth currently, what we see is binaries looking like this. Binary systems of two black holes that are roughly the same size as each other. And they're typically, basically a little bit heavier than the sun, or maybe a few 10 times, 30 times, 100 times. And the amount of waves they produce, the amount of energy released in these waves is really, really enormous. So when those two black holes crashed into each other right at the end and merged, the peak power output is actually bigger than the entire electromagnetic power output by all the observable stars in the universe. It's a lot of power. But by the time it reaches us 1 billion light years away and gets detected by this detector called LIGO, as I said, it's by the time it reaches us, it's tiny, really, 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 really tiny. These little oscillations I was showing, these little wiggles, are smaller than an atom, smaller than a proton. They're tiny, 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 tiny. And it's a remarkable feat of engineering that we can actually measure them. So what we're physically measuring is the stretching and shrinking of these two long arms. If you want to hear more about how this works, I encourage you to watch the talk that was recorded on Friday by Ian Jones. He has more of a kind of introduction to this aspect of gravitational wave astronomy. But we're measuring stretching and shrinking of these two arms. Each of these arms is 4 kilometers long, so it's pretty long. And we're measuring this incredibly, incredibly tiny stretching and shrinking. But the information we get out of that tiny, tiny little stretching and shrinking is a lot. We learn a lot about the universe around us. So as I said, traditional astronomy, we didn't know anything about black holes, or very minimally amount, about the black holes around us. Whereas now we know quite a lot, and we know there's a lot of black holes out there. So as I said, we've seen 100 of these signals roughly already, and our detectors are not as precise as they will be in the future, but we see these things all the time. There's lots and lots of black holes out there in the universe. As I also said, with traditional astronomy, we didn't really have an opportunity to say whether Einstein's theory of general relativity is correct in regions where gravity is really strong. We could only say it was correct in regions where gravity is really weak. But now that we've detected these things, we can say that Einstein's theory is completely consistent with everything we've observed in these strong gravity systems. Now, I also said that you don't always just have two black holes. You can have two neutron stars, very, very dense stars. Or you can have one neutron star, one black hole. And so by measuring the waves from those systems, we actually learn about what the composition of a neutron star is. It's got neutron in the name, so you might think it's just made up of particles called neutrons, but it's actually a lot of crazy nuclear physics going on inside of a neutron star, and we don't quite know exactly what its composition is, but we can learn about that from gravitational waves. Now, what might seem a bit weird about this whole thing is that unlike a telescope where we just see a visual image, with gravitational wave astronomy, that's not the way it works. With gravitational wave astronomy, we can only detect a gravitational wave. Sometimes we can just detect it because it's really, really big. We see these wiggles in the data. Most of the time, though, we actually have to go digging for it. We have to go into the data and dig out and find the signals that are buried inside just the noise of the detector. And certainly, once you have detected it, in order to say what created it, you need a very, very accurate theoretical model telling you, okay, if a waveform looks like this, what was the system that created it? So you need to basically solve the equations in Einstein's theory very, very accurately in order to say what created a given wave that you've seen in the data. Now, There might be something seemingly circular about this, because I'm saying we're testing whether Einstein's theory is right. Well, at the same time, I'm saying that we need to use Einstein's theory in order to say what created a given wave. So there's a lot of work that goes into looking at possible deviations from Einstein's theory and ruling them out, showing that they're inconsistent with the data that we find. So basically, they cannot create a wave that looks like the wave we see. Okay. Now, this is just stage one in a much bigger, decades-long plan. So currently, we've got four detectors working on Earth that are detecting these systems. We've got these two LIGO detectors in America, in the United States. We've got this detector Virgo in Italy. And just recently, this detector in Japan called Kagra has started operating. It's not yet actually detecting anything, but they're working on improving it so that it will. There's an older detector, Geo 600, that was just there to test technology. It's not good enough to actually detect anything. So we've got these four detectors up and running. Within the next decade, there's going to be another LIGO detector in India. They've already started excavating the grounds for that and building it. And in another 10 years or so, we're going to start building much bigger detectors on Earth. So in America, there's a plan to build something called the Cosmic Explorer, which is basically just LIGO, but 10 times as big. So rather than 4 kilometers long, those two legs we saw are going to be 40 kilometers long. And then there's another project in Europe called the Einstein Telescope, and it's a bit smaller, but a bit more complicated. Well, things are going to be even more ambitious than that, because we're not just putting these detectors on Earth, we are actually launching them out into space. So currently, the only one that's actually funded and is progressing towards being launched is this detector called LISA. And once you're out in space, you can make it really big. So these arms are not 4 kilometers long, they're not 40 kilometers long, they're 2.5 million kilometers long, which is about as big as the sun. And once you're out in space, well, you don't have all this noise from just, little gravitational movements all over the Earth. And so you can detect a lot more things that you wouldn't be able to detect on Earth. And there's other detectors also planned to be launched into space. One is called DeSiGo. That's a Japanese detector. And China is also planning actually 2 detectors in space. So once we have all of this stuff up and running, we're going to see a lot. We're going to see a lot more than what we currently see. We're going to see it with much greater precision, and we're going to see it much further away. So this is one particularly important system or kind of system that we're going to detect. So I showed you what LIGO sees as 2 black holes that are basically the same size as each other, and they're maybe as big as or as heavy as our sun, or maybe 100 times heavier than our sun. But these systems called extreme mass ratio inspirals, or EMRIs, they're actually going to be probing those supermassive black holes at the centers of galaxies. So these black holes that are, 1 million times heavier than the sun. And the systems we're going to see are little black holes that are maybe 10 times as heavy as our sun, zipping around those supermassive black holes at the center of galaxies. And these systems are very interesting because, unlike what I showed you that LIGO sees, where it's 2 things that are actually basically on a circular orbit getting smaller and smaller and smaller over a few seconds and then merge, what we're going to see with this kind of system is actually multiple years long. And these aren't simple circular orbits shrinking. These are very, very complicated orbits. And basically what we're going to see is this little guy executing hundreds of thousands of highly intricate orbits very, very close to this supermassive black hole. And it's basically serving as a probe, but it's probing the space-time around the black hole. And because it's lasting for years in hundreds of thousands of orbits, and because the orbits are very complex, the waveforms that come out are very, very complicated and contain a lot of information in them. And these systems are going to be detected by LISA. And as I said, we need theoretical models telling us what a waveform is supposed to look like, and also, given a waveform, what created it. And what that means is, to get all the information from this complicated waveform, we need a highly accurate theoretical model that's really accurate over, tens of thousands of orbits or hundreds of thousands of orbits, and maintains accuracy over that entire time. And that's where I come in. That's the field that I work in, modeling this kind of system. That's what all my PhD students do. That's what dozens of researchers do. Focus on this particular system because we get so much information out. I see I missed a question. The question was, so it works kind of like a sound wave, but with gravity. Exactly. Yeah. So a sound wave is a very good analogy for a gravitational wave. Okay, now it's important to get a sense of the scale here. I was actually working in this field for more than 10 years, I think, before I saw a picture like this that really made it settle into my head what we're looking at. So this is the same picture I showed you before that was seen by an actual telescope on Earth. And I showed you, these stars orbiting around. And from the picture, it looked like those stars were getting pretty close and then zipping around, going far away, coming back in, getting pretty close, zipping around. But the closest star, the closest approach it ever gets to that central black hole at the center of our galaxy, is about 1,000 times bigger than the size of the black hole itself. So on the scale of the black hole, it's actually at a very big distance. Whereas these EMRIs are really, really close in. So you'd have to zoom way, 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 way in to actually see these guys. And this is what you see. As I said, these are not simple circular orbits getting smaller and smaller. These are very, very complicated orbits. And very, very close to the big black hole. So we learn a lot about what the actual black hole is, whether it's described by Einstein's theory, whether it's the kind of black hole we expect to see. We learn a lot about a black hole from a system like this. In fact, we learn more about black holes than from any other system. Now, this is actually a very interesting aspect of Einstein's theory of general relativity. That we think of black holes as being these really crazy exotic things. It's just a region of gravity that's a hole. Once something falls in, it can't get back out. It seems like a crazy idea, but Einstein's theory actually dictates that every black hole we see out there, as long as it's not too dynamical, as long as it's basically in kind of a equilibrium with its environment. Every single black hole we see in the entire universe has a common, unique form. There's only one kind of black hole in the universe. And no matter what you throw into the black hole, no matter what the black hole was formed from, no matter what happened in its entire history, it still has this form. And the form is described just by two things: how heavy is the black hole and how rapidly is it spinning. So black holes do spin. They drag space-time around them as they spin. And every black hole in the universe, as long as it's in equilibrium, is described by just these two things: how heavy is it and how quickly is it spinning. So by actually observing this black hole with this supermassive black hole with this little guy zipping around and around and around, we can test, is Einstein's theory right? Is that black hole exactly of this unique form that Einstein's theory predicts? And this test is going to be much, much more precise. This is going to be a test of GR that's much more precise than any other planned test. Okay, now let's go back all the way to the equivalence principle. Now, I introduced the equivalence principle basically to explain why the curvature of this rubber sheet is determining how objects are moving on that sheet. But that principle is actually an approximation. It's not an exact statement. So let's say we've got this black hole, we've got this hole in the rubber sheet, and we've got, say, a little star going around that black hole. So previously what I'd said is, okay, if I give a little kick in this direction, it's just going to orbit around on this circle, and it's just going to go around and around and around. But this little star is actually changing the shape of space-time around it. And that change in the shape is actually altering the star's motion. It's not moving just on this circle going around and around and around. It's being influenced by its own effect on space-time around it. So this correction to the equivalence principle is what we call a self-force. It's kind of a force that the body feels because of its own effect on space-time around it. And so I'm giving the example of something really, really heavy, like a dense star, like a neutron star. But in reality, everything in the universe experiences this thing called a self-force. It's just that usually it's so tiny, we don't care about it. So as an example, if you have an astronaut just orbiting around the Earth, that astronaut does feel a self-force, but it's roughly 1/1,000,000,000 of 1/1,000,000,000 of the astronaut's weight. So small, you could never possibly care about it, and you can never possibly even measure it. But in these systems, in these Emery systems, first off, the force is bigger. It's not that tiny because this object is so dense. This little star is so dense. So it's much bigger than what the astronaut feels. But it's still tiny. It's still very tiny compared to the gravity of the big black hole. But even though it's tiny, just imagine at every instant along this orbit, you have a little tiny force. And so when you add up all those instants, that's accumulating to a big effect. So it's little tiny effects adding up to something big over the course of this in spiral as the small guy spirals into the big guy. And as I said, we need to model these systems. And so modeling them is very difficult because we need to model this tiny correction to the equivalence principle, potentially for hundreds of thousands or even millions of these extremely intricate orbits that I showed you. So what comes out in the end of the day? Well, another movie comes out. Okay, so this one is unfortunately a bit laggy, but you get the idea. You've got these incredibly complicated orbits, and it's getting smaller and smaller and smaller. The orbit is getting smaller. In the video, it looks like it's the black hole in the middle getting bigger. That is just the camera zooming in. The camera zooming in so it can still see the orbit getting smaller. So it's not the black hole that's getting bigger, it's the orbit that's getting smaller. So that is what we are trying to model with incredible precision. And that noise you heard was actually just a rescaled version of the physical waveform translated into sound wave. Okay. There's one more question. Are the orbits a chaotic system, or is there some sort of pattern behind it? So it looks pretty chaotic, but it is not chaotic. It's an example of something called an integrable system, which basically just means not chaotic. So it follows a very specific pattern. It's just very, very complicated. Okay, so this is what I want you to take away from this talk. We started off saying, what can we see with traditional astronomy? And we can't see a lot about black holes. We can't see a lot about really physics in strong gravity. But with gravitational wave astronomy, now we can really, really, really precisely probe physics in regions of strong gravity and specifically probe black holes. Okay, now next generation detectors are going to see a lot more. So far, all the systems we've seen are pretty similar to each other, unless they involve a neutron star. Usually it's two roughly equal sized black holes going around each other. But we're going to see a lot more pretty soon. And one of the things we're going to see is those emeries that I showed you. And those are particularly precise probes of the supermassive black holes. So remember that those supermassive black holes at the centers of galaxies, those were the real first evidence of real existing black holes in the universe. But we could only infer that they were there from how things were moving around them. And we couldn't infer it very precisely. Whereas with gravitational waves, with emeries, we're going to get incredibly precise description of those black holes at the centers of galaxies. And tying this into really the basics of Einstein's theory, in order to detect these waveforms and extract the information that they encode, we will need really incredibly accurate calculations of these tiny, tiny corrections to what we think of as one of the core principles of Einstein's theory, which is the equivalence principle. Okay, and I will end with an analogy. So, this is a movie I saw with my father in the 1980s. I don't remember how old I was, but as you can tell, it's a movie about a black hole. It's a movie made by Disney. And when I saw this movie, I thought, wow, black holes are pretty crazy. What I learned later is, well, this is not really necessarily the most realistic depiction of black holes. But it's pretty good. You can't blame Disney too much. And remember, this was before we'd actually observed a black hole in the universe. So I think movie makers were feeling pretty good about just making up whatever they like. So this is kind of the situation that we had decades ago. Black holes were a theoretical concept. We couldn't see them. We didn't know if they really existed. They were just fancy science fiction concepts. Now we flash forward 30 years, and I go to see another movie called Interstellar. And there is a much more precise depiction of real physical black holes. This one, still not 100% accurate, but much, much more accurate than what we had 30 years ago. And this is really reflecting how real black holes are in our mind as time progresses. They went from something totally theoretical, that were just wild concepts, to something that we now know is all around us. Every galaxy has got a massive black hole at its center, or almost every galaxy. And there's just black holes zipping around all over the universe. Okay, so I would like to end it there. No more questions currently. So if you do have questions, I'm happy to answer them. We do have another half an hour in this time slot, if you would like to ask any questions. Okay, if we don't have questions, thanks again for attending. I hope you enjoyed the talk. The talk will be available in recorded form, I think indefinitely. So, please share it with your friends if anybody's interested. I would like to say a few words before we wrap up. I think I'm waiting for a closing slide here. So, before you go, we do want to know your thoughts about this event. We do want to know how well we're doing. So if you have a chance, please do share with us your thoughts and let us know how we can improve future events. So you can do that by taking this survey at this address here. You can scan this with your smartphone or just type in this address. There should also be a link in the chat for you to click on if you'd like to use that instead. Okay, we do actually have one more question. That bit about self-force, does that mean that it's impossible to hold a stable orbit around a black hole without extra energy? Yes, 100%. Yes. Yep. So the self-force is taking energy away from the orbit, and that's actually what's causing it to spiral into the big black hole. And yeah, so if you want to have an eternal orbit just going around in a perfect circle forever, for example, you would need some other source of energy pumping into that orbit to keep it on that circle. Excellent question. Okay. I think we have one more closing slide. So yeah, as I mentioned at the beginning, this event is part of a much bigger festival, the Southampton Science and Engineering Festival, which we also call for short SOTSEF. This is taking place, started last Friday. It runs until the 20th of March during British Science Week. And there's a lot to explore, so I do encourage you to explore. We have one more live talk from the university's mathematics department later this week, as well as the recorded talks you can watch from last Friday. And we have live events on campus if you're able to visit campus. So please visit this address, www.sotsef.co.uk, in order to look at the full schedule of events. Okay, thanks again for attending, and I hope you enjoyed the talk.